Today, the technique we're going to be working with is the Agarose gel. We're going to be pouring Agarose gels into these gel trays, so we're going to be learning proper technique for sealing them before pouring the molten Agarose in. We're going to be learning about removing the combs to produce proper wells, removing the tape to allow us to electrophoresis things through our gel, and we're also going to be learning a little bit about how to load our gel properly. Today's video, we'll be discussing how to prepare an Agarose gel for DNA electrophoresis. We're going to be using plexiglass gel trays, just like this one, and sealing them with lab tape. There are other systems available, perhaps with a rubber clamping system or some other gasket, but we're going to be old school, we're going to be using tape. Now, the largest problem that students have with this lab is doing an inadequate job at taping the gel tray. When they pour in the molten Agarose, it immediately leaks out. If too much leaks out, there isn't enough room to place the samples into the gel for electrophoresis. That requires us to remove the gel, clean the tray, retape the tray, get more Agarose, pour the Agarose, and wait for it to solidify again. Bit of a time-consuming process, and it actually delays people getting out of the lab on time sometimes. So I'm going to show you the method that I use to tape up the gel tray that seems to be reasonably bomb-proof in terms of leaking. So what you're going to want to do is make sure your gel tray is clean on both ends. It shouldn't be an issue. What you want to look for is things that might interfere with getting a good seal with the tape. You're going to need 2 pieces of tape long enough to cover either end of the gel tray. So you can just eyeball it. 1 piece of tape, 2 pieces of tape. All right. Now, once you have your pieces of tape, we're going to be placing them on the end of the gel tray. What I like to do is to place the tape on in such a way that it contacts, of course, both the bottom of the gel tray and both sides, leaving a bit of an overlap on the back. Maybe it's easier to see if I put it in this direction. So you can see the tape overlaps the bottom of the gel tray. At that point, then fold the tape over. You may have noticed I've made sure the tape makes contact on all 3 sides here. Once this is folded over, do the same procedure on either end. Well, we have what is called hospital corners. If we then fold this over, you can see we've got a nicely sealed end to that gel tray. Simply repeat the procedure on the other end. And there you have it, a sealed gel tray. Now, before you pour in your Agarose, you might want to decide where you're going to be placing your comb. Typically, they'll be on our gel trays, there's comb holes on one end, there's comb holes in the middle, and there's 2 sets of each. We're only going to be running enough samples to use 1 comb, so typically we're going to be using 1 comb at the top of the gel and electrophoresis the DNA down the full length of the gel. If we had a large number of samples that we didn't need to run through the entire length of the gel, we could of course place another comb here to double the number of wells we had available for samples. But we're not going to do that. I'm going to put it up here. Now, a couple of things. Molten Agarose. You'll notice I'm working on one of these metal trays. This is just in case the gel leaks. This gel tray leaks. The gel will be contained. It's a lot easier to clean up. It makes things a little bit easier in the lab. Now, you will have been provided with a pre-measured aliquot of pre-made Agarose in TBE buffer. Now, the Agarose solution we're going to be using is 0.5%, and what's usually referred to as weight per volume, although more correctly it would be mass per volume. What 0.5% means is that we have half a gram of Agarose dissolved into 100 mils of TBE buffer. You're going to be using about 60 mils. That's about the adequate volume to fill the gel tray to a depth that will allow us to put samples into the wells that are created by our comb. Now, I mentioned TBE buffer. That is one of a few buffers you can use for DNA electrophoresis. TBE stands for tris, borate, EDTA. Tris is a buffering salt, which is actually fairly basic. The borate is boric acid. This is what's added to the tris to create the buffer solution and actually bring the pH of the solution into a more neutral, actually only very slightly basic position. EDTA, the last letter in the acronym TBE, is a chelating agent. What a chelating agent does is it mops up and binds to divalent cations. A lot of DNA degrading enzymes use divalent cations as a cofactor. So by removing the divalent cations from solution, we can prevent breakdown of DNA by these enzymes. So once you've got your aliquot of agarose, which you've got your taped gel tray, you've got your comb in place, you can simply pour the agarose solution into the gel tray. Be gentle and pour from a low position so you don't create bubbles. If you do create bubbles, it's actually fairly easy to take a pipette tip, move them to the side, or pop them. Bubbles will interfere with the passage of the DNA through the agarose gel, so you do want to prevent them if possible. Now, there is one other solution inside our TBE agarose, and that is CyberSafe. What that is a dye which will bind to the DNA as it travels through the gel. This dye is not visible necessarily at the concentrations we're going to be using it to the naked eye, but it does fluoresce under ultraviolet illumination. So once we finish running our agarose gel, moving the DNA into the gel as it picks up the dye, we can then remove the gel from the tray, place it under UV transillumination, and our DNA will glow, and we'll be able to take adequate pictures. Now, what you're going to want to do is leave this gel tray in position without disturbing it long enough for the agarose to solidify, and this happens as it cools down. What you may notice is that the gel will go very slightly opaque as it solidifies. One thing you do not want to do not remove the gel comb early. If your gel is not fully polymerized, fully cooled when you remove the gel comb, the wells will collapse and you will not be able to add your sample. What we're going to do is we're going to leave this to solidify for a period of time. We'll come back, we'll remove the comb, we'll remove the tape, and then we'll talk about loading our agarose gel. We've left the gel sitting for about 10 to 15 minutes. If you look very closely, you might be able to see that it's gone very slightly opaque. I'm sure it doesn't show up very well in the video, but you will definitely be able to detect this by eye. We now want to be very careful with this gel, particularly a 0.5% gel. It tends to be very fragile. A 2 or 3 or 4% gel, a lot more robust, can be handled a little bit more vigorously. So, now that our gel is fully polymerized, we can remove the comb. You'll be able to see a series of wells, indentations in the gel, and because we've waited long enough, they've remained open. They have not slammed shut. The next step is to remove the tape. Now, this seems fairly straightforward, and in fact it is, but one thing you want to do is make sure the gel does not slide out of the gel tray. This is another common mistake by students in this lab. If you have a look, you might not be able to detect this right away. I'm manipulating the gel in such a way that the gel doesn't have an opportunity to slide out of the gel tray. If it does so, it will hit the ground or the tape bench, it will break, and you'll have to do a new gel, unfortunately. So, because we're wearing gloves, we can handle the gel to some degree. If we're moving around the lab and we want the gel to not slide out of the gel tray, it's very easy to hold the gel like this with a thumb and a finger on either end so that it can't actually slide out of the gel tray. Without the thumb and finger, tilting the gel a little bit, it immediately starts to slide. Now that we've removed the tape and the comb, the next step would be to place this gel into the gel running apparatus. So plastic box, black box about yay big, and add TBE buffer to the depth of a couple of millimeters above the surface of the actual gel. This buffer is going to be able to enable us to pass a current through our gel. Now, for the next couple of steps, I'm actually going to demonstrate this basically on dry land without putting it under the buffer, because it actually is quite difficult to see once it's under the buffer. If you imagine this is our DNA sample, it's a small amount of colorless liquid in a basically aqueous solution. If we were to try to load this directly into a well under a certain amount of TBE buffer, two things would happen. One, we wouldn't be able to track where our sample has gone because it's colorless and so exactly the same as the buffer that we're trying to pass it through. And two, because the density of this sample and the buffer is very similar, both being pretty dilute aqueous solutions, our sample would simply float out of the well. To fix this, we're going to be using DNA loading dye. Basically, it's a colored solution with a dye that will travel through the gel, similarly to the DNA, and a densifying agent, usually glycerol or phycol, that will provide enough density when mixed with our sample that our sample will be able to drop to the bottom of the well and won't significantly mix with the TBE buffer that the gel is sitting in. Now, generally these loading dyes are supplied to you at a 4, 6, or a 10x concentration, which means that you were to mix them 1 in 4, 1 in 6, or 1 in 10 with your sample prior to addition into the wells of your gel. There's a couple of things that will make this process a little bit faster for us in terms of loading the gel. One is to know that it doesn't really matter that you get this exactly down to 1x with your sample before loading it on the gel. The second is a little trick in terms of mixing samples and buffer together, or pardon me, loading buffer together. What you want to do is grab a hold of one of these parafilm squares. It's basically a thin sheet of paraffin wax. You have these in your locker. Rather than measuring out exact quantities of loading dye, I'm simply going to take up a volume of it into a pipette, a Gilson, and I'm going to apply small-ish drops to the surface of the parafilm. And I'll make as many as I have samples, plus a couple of extras. Now, I don't know exactly what the volume of each of these drops is, probably somewhere between 2 and 5 microliters. Now, let's say, for example, I wanted to load 5 microliters, 6 microliters, or 10 microliters of my sample mixed with loading dye into this gel. I'd simply set my pipette for, let's say, I want to load 8 microliters of my sample in each well. I'll simply set it to 8 microliters. There we are. Well, I'll get a pipette tip, which will make things much quicker, obviously. There we are. I'll take up 8 microliters into the pipette tip, and I'll dispense it into one of these drops. You'll see that the sample and the dye will mix together. You can actually do a couple of up and down pipettings to make sure the mixing is fairly thorough. And then by depressing the plunger on your Gilson past the normal stop point, you can take up the entire dot, including the loading dye. All right? In order to dispense all of this, you're obviously going to have to depress the plunger past the normal stop, just as you did to pick the sample up. You then place the tip into one of the wells. Now, this can be a little bit tricky when it's under a bit of buffer, but there are some high contrast red lines underneath the gel in the apparatus that'll make it a little easier to see, and you can move back and forth to get the light in the correct orientation. But basically, you add a sample into the well, depress the plunger all the way, and there we have our first sample deposited into our Agarose gel. We would repeat this for all of our samples, the same trick with the paraffin, and add a a DNA marker. We would then affix our electrodes and run a current through this and monitor the progress of our DNA through the gel by watching the distance that the dye has moved. The dye will move usually ahead of most of the bands of DNA, depending on their size, obviously. For our purposes, once the dye has moved between half and 3/4 of the way through the gel, we will be able to take a picture and determine whether our PCR or our plasma digest has been successful.